Hello, Principles of Technology. Today we're going to take a look at pressure in a fluid column. First, we're going to look at some background information. Then we're going to see how this applies to everyday life. And then we're going to go take a look at how pressure affects us and how we can use the formula. So here we get started. So here's our background information. Remember that we looked at pressure a few days ago, and we found that pressure is force per area. That was the definition. And the definition really tells us how the formula works. We have a force, we divide it by the area that the force is affecting, and we find our pressure. So it's pretty straightforward. The question is, if I was in the water, say I jumped into the bottom of a pool, how does this formula work? I can feel the pressure on my ears. But how does this formula work? Well, I'm going to show you this in an illustration. In this picture, we can see that air pressure is 14.7 pounds per square inch at sea level. And if we look at our little globe on the left here, we can see that if we take a 1 square inch area of our atmosphere and extend it from the surface of the ocean all the way up to the edge of the atmosphere, so go all the way to space, we'll find that the weight of the column of air and all the other stuff that's in the air around us weighs about 14.7 pounds at sea level. So the big question is, why the heck do we need to know that? Who cares? We already live in it. It's already here. What's the big deal? Well, all of us like to drink some water once in a while. And water in our town is supplied through a gravity system and through pipes. The illustration you see here is ductile iron pipe. It's very common. That's what cities use to supply water to homes. So basically, we put a tank on a hill and we use gravity to feed the water from that tank to our homes. But if the pressure is too great, we can blow the pipes apart. We can blow our faucets apart. Imagine turning your water on and having the water pressure so high in your home that it rips the cup out of your hand. And then you can't shut it off because the valve at the sink isn't strong enough to shut the pressure off. So it's very important to understand how much water pressure we have by placing our tank on a hill, and where do we put that tank so we have water pressure throughout our town that is safe and easy to use. So here's some questions. First, does pressure change at sea level as the area increases? Before I answer that, watch this brief video. So the question is, does pressure increase as area increases? And we're going to find out right now. So imagine we're going to take a ruler, and on the earth, I'm going to make a 1 square inch piece. And on that square inch piece, I'm going to put 14.7 pounds. Now, what's interesting about that is that's the same as our air pressure. So the question really is, does pressure increase as area increases? Well, if I take that square inch and I make it, say, a square foot, and each square foot has 12 inches going this way, and there's 12 square inches going that way, for a total of 144 of these little squares. And we know from previous notes that there's 2,117 pounds on that square foot. So, does pressure increase as the area increases? You got to be saying absolutely yes. Because look, the numbers are different. This one's really small, that one's really big. Well, the numbers aren't complete without the proper units. This is 14.7 pounds, but it's 14.7 pounds per square inch. This is 2,117 pounds per square foot. This bottom number in our denominator, or our unit, makes all the difference in the world. This is one little tiny piece. If I keep adding these up, there's only 14.7 here, 14.7 there, 14.7 there, 14.7 there, and so forth, 144 times. What increases is the force on the ground increases as area increases. So you have to think of it this way. If you took this number and ran it through a calculator, so let's do that. Let's take our 2,117, divide by 144, because there's 144 of these little square inches in this square foot. What's this number end up being? Well, if I hit equals, it's 14.7. And that is what's on 1 square inch. So if I take 14.7 times 144, you're going to find out that it's 2,117. We just rounded up. So yeah, there's 2,117 pounds here, but the pressure remains the same. It's still 14.7 pounds per square inch or 2,117 pounds per square foot. We have to keep in mind these units on the bottom of that fraction are extremely important. So keep that in mind that as area increases, the pressure stays the same, but the force will increase. Hope that clears some things up. So from the video, we found out no, pressure does not increase as area increases. The pressure remains constant. What does change, remember, as the force changes. The force goes up as the area increases. Our second question, and I want you to think of this for a minute. If I'm deeper into a fluid, does the pressure increase? Well, remember from our previous illustration that air pressure is created by a column of air. And we discussed this in our last video, or our last notes, that if I stand on the top of Mount Everest, remember I have less air pressure because the column above me is less. So the answer to this question is yes. As depth increases, so doesn't the pressure. And that's what this is saying. And we can actually accurately calculate this if we take a look at it. So as the deeper I go in a fluid, the more pressure I'm under. And if you think about it, if I jump into a pool and swim to the bottom, I can feel pressure on my ears. That is because there's more water above my head than there was when I was at the surface. So the big question is, how do we calculate this? Of course, there's a formula. The formula looks like this. It's P equals rho W times H. Well, I hate trying to remember that it's rho W because that funky looking P is the Greek letter rho. So I like to call it funky PW. It's just much easier to remember than a rho W. So P equals funky PW times H. Our thumb chart for this looks like this. We have P on top, our funky PW on left, our H on the right. And remember, the funky PW and the H could be switched left to right. It really doesn't matter because our vertical line is multiply and our horizontal line is divide. So that makes it pretty straightforward. So let's take a look at the whereas for this. The funky PW is the weight density of liquid. And these are constants. These are things that we can look up in a book. Water has 62.4 pounds per cubic foot. So those are important information to know. And we know also that newtons per cubic meter is also our other weight density for the SI system. If we took a look at H, H is the liquid height or the height of the liquid above where we're measuring. Remember, that's always up, not down. And lastly, P is pressure. And pressure is still going to be in pounds per square foot, newtons per square meter, or pounds per square inch. And I just made a note here that that funky P, we're not going to call it rho, we're going to call it funky PW because it's easier. So this formula is kind of funky. We're throwing a lot of verbs here and a lot of different things at this. So let's take a look at a couple problems. And again, I'm going to use my 6 steps to solve these problems. So here I'm going to take a look at my question and I'm going to say, hey, what am I looking for? Well, I'm looking for pressure. And it says right there, what is the pressure at the bottom of the column? So knowing that I'm doing with pressure at the bottom of a column, I'm going to use this formula. That's step 2. What is my formula? My formula is P equals funky PW times H. So next I need to plug my numbers in. Do I have a weight density? Now remember, weight density is something in a pressure per cubic something or per volume. And if I look at this question, I see that 7 newtons per cubic meter is the weight density of the fluid. And I see that H is 8 meters. So I plug those numbers in, I get this. Now the one thing to keep in mind when we look at our units in step 4, are my units correct? They are. Remember that the meters for 8 meters is on the top of our fraction, and that cubic meters is on the bottom of our fraction for 7 newtons per cubic meter. With scientific notation, which that number 3 is our scientific notation, remember we cancel out the meters on the bottom and we cancel out one of the meters on top. And when we do the math, we end up with 56 newtons per square meter. So our units do work because we do end up with a pressure. We just have to keep in mind that with scientific notation, when we get rid of our meters on the bottom or our feet, if it's in cubic feet, we subtract from the 3, we subtract 1 to get 2. And that's how we get 56 newtons per square meter. So that was pretty straightforward. Let's take a look at another question. Again, I'm going to use the 6 steps to do this. And I want to take a look at our solution. And our solution is, what am I looking for first? Well, I'm looking for pressure. And if I look at this, we know that pressure is force per area, or funky PW times H, depending on what we're using. And because we're looking at a water tower, we're probably going to be using that funky PW times H. So now that we have that, do I have a weight density of our water? And remember I said before that weight density is 62.4 pounds per cubic foot for water, and we see that in our question. We also see the height of our tower is 150 feet. So now that I have those two numbers, I'm going to take those two numbers, I'm going to plug them in, I'm going to check my units. Step 4, notice that feet is on top of my fraction and cubic feet is on the bottom of the fraction. So we are going to subtract one of those to get pounds per square foot. And there's our answer. Now that's kind of a scary thing. 9,360 pounds per square foot. Is that too much water pressure to be safe in our water system so that our ductile iron water pipes don't come apart? So let's convert that. Let's take a look at our problem number 2 and convert that to pounds per square inch. And to do that, we have to remember that the answer from our previous question is 9,360. And I'm going to need to know how to convert that pounds per square foot to pounds per square inch. And the solution for that, and this is the long way around, is this. I don't want you to write that down. I don't want you to understand that at all. That's really confusing. That's called a conversion formula, and you have to do all this cross multiplying and dividing and subtracting and getting all the units to work. So we're going to use a thumb chart for this. And our thumb chart shows us that if I have pounds per square foot and I divide by 144, I end up with pounds per square inch. Remember, cover up the PSI because that's what you're looking for. So if we cover up PSI, we take that 9,360 pounds per square foot and divide by 144, we end up with 65 PSI, which is well within the 35 to 100 pounds per square inch that most city water systems operate under. So that's pretty cool. So that system actually worked. So there's our formula for converting pounds per square foot to pounds per square inch, or pounds per square inch to pounds per square foot, depending on which way you want to go. Make sure you get that thumb chart and that conversion formula into your notes onto our conversions page. Let's take a look at one more problem. So this one's a little funky, and notice I've already put up the thumb chart for this because there's a hint there. We're probably going to need to rearrange this formula. So what I'm looking for is how tall is the roof? Well, we don't have a formula for height, but if I read the question, and this is one of the first times we're actually going to read a question first, I see that I have pressure and I see that I have weight density. If I have weight density and pressure, that's 2 of the 3 variables in the P equals funky PW times H formula, which means we're looking for H. So our solution is going to be a hint to rearrange that formula and to rearrange that formula so that H equals P divided by funky PW. That is true. We know pressure and we also know the weight density of the water. So knowing that, we can plug our numbers in so that we see that we have our pressure on top of our weight density. And when we do that division, we find out that our roof is 10.5 feet tall. So all we did there was rearrange the formula to solve for one of our unknowns. I hope this helps. Please, as always, contact me with questions, comments, concerns, or violent disagreements, and I look forward to helping you.